Hello everyone, my name is Sithi. I teach physics and do research in physics at Universiti Malaya. So what exactly is physics? Physics is the study of matter, its motion through space and time, and it involves the concept of force and energy. Physics covers a wide range of phenomena, ranging from the size of viruses and bacteria up to what we experience every day and to the scale of the solar system and beyond. Over the years, we have explored these wonderful phenomena using concept of mathematics, and we have understood so much about these systems. We know how a bacteria moves. We know how to use the concept of force to achieve maximum performance when we do our daily tasks. And we also able to predict the seasons, the motions of the moon, the planets, and the stars. So much we have gained in this area of physics, but we ask the question, does laws of physics applies to all scales? So this is a question that has been pondered over hundreds of years, perhaps thousands of years, and the early period of exploration of the physical universe started with this idea of classical physics. Classical physics involve phenomena that we can observe in our daily life, that we have a sense of experience, we can measure the important parameters, and we can derive the laws. So with classical physics, we have achieved major development in the area of technology and also able to understand how the universe works. But then, what if you push the size of the system to a very small scale, up to the scale of atoms or subatomic particles? And what about when you force the particle to move at a speed which is very, very fast? Perhaps faster than speed of sound, approaching the speed of light, which is about 300,000 kilometers per second. Then scientists observe there are deviations in the prediction of these theories. So one of the deviations is observed when the size of the particle goes to a very small scale, and this gives rise to the concept of quantum physics. On the other hand, when the speed of the particle moves to a very high magnitude, so you have effects that are not explainable by the theory of classical physics. So we need to introduce the concept of relativity. The development of classical physics took a very long time, about 3,000 years, and what we have achieved so much. And classical physics is able to explain a lot of phenomena, and this is thanks to the work from various scientists. The names include Copernicus, Galileo, and Newton. But what exactly is the issues that requires us to revise the classical physics? What were the fault lines in the theory that requires revision of these well-established 3,000 years old concepts? Essentially is delivered by the light. First, the warm bodies emits radiation. We call these black body radiations. And the spectrum of these lights, that is the distribution of the intensity over different wavelengths, follows a certain distribution. It is sort of like a hump. And classical theory could not explain this distribution over the whole period of wavelength. The success of classical theory very much is about in the very low wavelength, large wavelength in fact. And the second experiments that create a second blow to this classical theory came from the structure of atom. Lights emitted by gases, atomic gases, showed in addition to a continuous distribution of light, it also exhibits unique discrete lines we call the line spectrum. Classical theory could not explain the origin of these discrete lines. And thirdly, when light shines on surface of metals, electrons are ejected out. This is called the photoelectric effect. And a classical theory assumes that if the intensity of light is large enough, there has to be electron emitted from the metal. But experiment shows only light with certain wavelength, shorter wavelengths, is able to emit photoelectrons. So these are the three experiments that created the major revision to the classical theory. A new theory is needed to explain this phenomenon. There comes the revolutionary idea proposed by Planck when he suggested that the light energy is quantized, meaning it comes in packets of energy. This is very much contradicting to the classical idea where energy is continuous. But Planck's model able to explain the distribution of radiation coming from hot bodies almost perfectly to the extent that it astonished Planck himself. The next contribution comes from Bohr, who suggested that the atoms could be like a miniaturized solar system, where the electrons move in a rather precise orbits, and light is emitted when the electron transits from a higher energy to a lower energy, and the energy emitted are quantized. And Bohr's model able to explain the discrete lines that were observed. Then come the master of physics, Albert Einstein, to explain the photoelectric effect. Einstein assumed the light is composed of packets of energy called photons. And again, the energy is quantized with energy E equals to Planck constant H multiplied by the frequency of the light. So you see, in all these three examples, the common idea proposed is light energy is quantized. And this is not the end of the story. In fact, the 20th century, that is from the 1900s, there were many attempts to explain other possible outcomes of quantum behavior. One of it is the particle-wave duality. This may sound strange to a classical physicist. How can a particle behave like a wave at the same time? But this is what proposed by de Broglie, who assumed that a quantum particle can exhibit both particle and wave behavior. And you can use experiments that has been widely used to study waves, such as double slit experiment that shows interference pattern. And if you shoot a stream of electrons, you will see the interference pattern, hence proving that electrons indeed behave like waves. The next experiments that prove that particle also exhibit uncertainty principles. In this case, when you observe a quantum particle, they are disturbed. Just like human beings, when you keep staring at people, people will behave differently. So this is observed in quantum particles. Therefore, the quantum particle loses the precision of its behavior. For example, when you observe the particle precisely in position, you probably will not be able to capture the momentum accurately. And this has been caricaturized through the cartoons and many stories that proposer of this uncertainty principle, Werner Heisenberg, was stopped by the police and he was asked, "Sir, you know how fast you were traveling?" And Heisenberg answered, "No, but I know where I was." So this is basically the idea of uncertainty principle. You cannot measure the position of the particle accurately, and the momentum of particle accurately at the same time. You have to give way one or the other. And the next properties of interest is the probabilistic nature of the orbits. Remember, when we talk about the Bohr model, a miniaturized solar system, the orbits of the electron are very precise. But Schrödinger proposed that the electron's orbit is merely a cloud of distribution of particles at a different position at a different time. And he introduced the idea of wave functions. And wave function satisfies dynamical equations called the Schrödinger equation, just like a classical particle follows the Newton's law of motion. Okay. And finally, I would like to talk about the properties that also intriguing, that a quantum particle can tunnel through a barrier, which a classical particle can only hop over. So this phenomena has been used for various applications, hence demonstrating that quantum particle indeed tunnels. For example, the tunneling diode is essentially a demonstration that particle indeed tunnel. Other example includes radioactivity, where alpha particle can tunnel through the nucleus barriers. So there have been a lot of applications of quantum physics. I will state two which are very practical in our daily life. First is semiconductor. I'm talking and my image is captured by the CCD camera thanks to the semiconductor, and a computer is analyzing this presentation also thanks to semiconductors. And we have light in this room emitted by LED light and other LED type lights thanks to the success of quantum theory for semiconductor. Another example of success of quantum physics is demonstrated in lasers. We see lasers almost everywhere. You see lasers now, in fact, in my hand. And laser is important for communication in optical fibers. And we have seen all these examples of applications of quantum physics in many, many different systems. So what is the issue now? So this marks the quantum revolution 1, where the idea of quanta was introduced, various properties of quantum systems was discovered, and a whole range of applications of quantum physics was demonstrated. But now we would like to talk about what is quantum revolution 2. Quantum revolution 2 is essentially about information. Remember when I said that a quantum system has a wave function? In fact, that is the state function which can be used to encode information. Just like in a classical physics, when you have the on button and you have an off button, these are the two states in classical physics. And you cannot have this on and off together simultaneously. But in quantum system, if you prepare a system in on state and also in off state, it can take these two states together. And this concept is called the quantum superposition. And this gives enormous resources for quantum information processing. For example, for classical bits, you have two states, 0 and 1. But for quantum systems, you have 0, 0, 0, 1, 1, 0, and 1, 1. So you see, for two states, you are able to have 4 possible quantum states that can be combined to form a superposition state. And imagine if you can have hundreds of qubits or even thousands of qubits, you can enormously boost up the computing capability of quantum systems using quantum systems. The next property of interest is quantum entanglement. The concept of entanglement is even more intriguing. For example, if I prepare two quantum systems and I separate them over a great distance, you will see that the quantum behavior is intact. So if I measure one property of the particle in the other end, the other particle will experience the quantum property that is designated to itself. Okay. So this is something intriguing. How can the signal travel between two far separated particles communicate between each other. And these properties, despite its weirdness, is the one that going to be used for quantum security applications such as cryptography. So now we talked about the possibility of using quantum systems for information processing using quantum superposition to generate lots of qubits that can be used for computing, and secondly to use the entanglement property so that it can be used for security and communication purposes. Now we ask the question, so far so good, it sounds quite interesting, but how are we going to produce these quantum bits or qubits? There are many systems that can be used to produce qubits. For example, if you have an atom that are in two different energy levels, these energy levels constitute the states. So if you can lift up electrons from one energy level to another level, so you can have excited states and also the ground state. So this serves as example of qubits in, for example, in systems such as in quantum dots and also in superconducting loop, which is essentially a loop that has a current that moves in clockwise direction or anti-clockwise direction. But in fact, there are lots of systems that are being considered as candidate for qubits. Defects in some lattices can also be used as quantum states and be used for encoding quantum information. So there are challenges that comes with dealing with quantum system. For example, the quantum properties can deteriorate, what we call decohere, when it interacts with noise or fluctuation from the environment, or even when it interacts with instruments or other environmental variables. So there are many challenges that we need to overcome to realize the quantum technology. But that is not stopping many industries, businesses into looking at the future applications of quantum computing and quantum communication. For example, quantum computers will be used to solve problems such as protein folding, search engines, detecting anomalies in astronomical data in experiments such as particle accelerators. It will be used to solve very difficult problems because of its enormous computing capabilities. On the other hand, quantum cryptography or quantum entanglement can be used for secure communications between states and also for the privileged nations. The landscape of quantum technology essentially falls in three different areas. One is developing new hardwares to encode the information in qubits. There are many systems being explored, such as organic molecules, things that can be easily managed, such as the photonic systems. And the next stage of development is to focus on algorithms. There are many companies being set up to focus on development of algorithms. And finally comes the applications. Many companies such as IBM, BMW, Volkswagen, the big pharmaceutical companies are also taking interest on quantum technology because they are preparing for the niche application that would come when the quantum computers are realized in the next 5, perhaps 10 years. But these are the gamble that many companies are taking because they knew that the returns will be worth the investment. So now, what is the message that we need to take forward? We need to improve the quantum science and technology literacy. We do not see this much happening in our country. The quantum physics is still being taught as a small chapter in high schools, and the universities also it is not being stressed as the potential for next generation applications. So I hope this talk gave you some idea about what is the quantum revolution 1 And what is the quantum revolution 2, which is essentially focusing on quantum information. And we should not forget that classical physics is not being swept away. Classical physics is still valid to all the scales that we experience today. You drive your car based on classical physics, but you may be using ways or routing system that may use quantum computers to find the optimal route to your destiny. So I hope there will be growing interest among young people, students, and even general public to explore the wonders of quantum science and technology. There are plenty to come, and I hope that we can equally be part of these major revolutions that is happening at the moment.